we have come down to the pixel density and refresh rate of the universe, the Planck scale. So we can talk about the Planck scale, which I think is super interesting. There's this idea in science that reducing everything to its basis will give us the truth of how it functions. Does that make sense? So like if I can take this glass of water and understand it at its basic molecular structure, that will help me understand the truth of how that
How it
functions,
holds water. Yeah.
how we interact with it, all those types of things. So we've continued to go down this scale of atomic particles, right? We talked about the three infinites. The cosmos is infinitely large. The atomic scale is infinitely small, and the human cell is infinitely complex.
Mm-hmm.
Well, we're talking about the atomic scale here. So going down into the infinitely minute aspects of the universe, which is the Planck scale. So what we essentially found is that there is a maximally small level that we can reduce all things down to. It's called the Planck scale. Okay. So the Planck scale resides at, I have the mathematical equation for anybody that's curious, 10 to the negative 33 centimeters for size and 10 to the negative 43 seconds for time. Okay. This is like essentially as low as we can get. So the Planck scale, characterized by Planck length and time and mass energy, serves as a theoretical boundary where our current understanding of physics, particularly the classical concept of space and time, begins to break down. This scale challenges the notion that space-time is fundamental. Continuous fabric of the universe is suggested by classical physics and general relativity. Here's how the Planck scale contributes to the argument that space-time might not be fundamental. Okay? Quantum gravity effects at the Planck scale. The effects of quantum mechanics become significant in the fabric of space-time itself. Quantum fluctuations are expected to be so intense that they significantly distort the space-time continuum, leading to what is often visualized as a foamy structure. This foamy aspect implies that space-time is not smooth and continuous, but rather dynamic and granular at extremely small scales. So I was curious, what does foamy matter of the universe mean? And so I essentially dug into, what does that mean? What does the foamy matter mean? And it led me to what's called, you don't have this, sorry, Heisenberg's uncertainty principle. Okay, so is a fundamental concept in quantum mechanics formulated by Werner Heisenberg in 1927. It fundamentally challenges the classical notion that we can measure the properties of particles with arbitrary accuracy. This principle states that there are inherent limits to the precision with which certain pairs of physical properties of particles known as complementary variables or canonically conjugate properties can be simultaneously known. Essentially, what the Heisenberg uncertainty principle says is that we cannot measure all parameters of a particular particle at its base level. You just can't. They have to be measured independent of each other, and you can't measure them together. When you measure one, it stops the progress of the other side, which is a super strange concept. But the Planck scale kind of runs into this same issue, where we get down to this level where all sorts of crazy stuff in space-time starts to happen. We see like miniature black holes that appear on and off. We see like a fuzziness of, clarity in different areas. We see time not holding true in certain experiments, that it's not linear and things are moving at faster than the speed of light, which Einstein said in the theory of relativity would be impossible.
Yeah.
Because as an object approaches the speed of light, mass becomes infinitely dense.
Yeah.
So it requires infinitely more, propulsion or energy in order to get to the speed of light, which would make the speed of light impossible to travel. So these things start to break down. What's interesting to me is after studying the effects of the Planck scale on space-time, What it felt like to me is we have come down to the pixel density and refresh rate of the universe. Because that's essentially like what they're seeing, is they're seeing that pixels are coming and going in different parts of the universe with no rhyme or reason. And they can't get a clear view of the baseline of these things because like they're viewing it in time frames that are too quick for the universe to render. Pixel rate, pixel density, refresh rate. That's what came to my mind when I was studying Planck scale. I'm like, wow, we literally found the pixel density and refresh rate of the universe at the base level in space-time. But what does that tell you then? When you're looking at a screen that has pixel density and refresh rate, is that the truth of all things? Yeah, pixel density and refresh rate.
You know what's funny is look at the bottom right of that screen.
Yeah, it's pixelated. Yeah. But when you think about that, when I'm looking at a screen that has pixels and refresh rate, is that the truth of all things? Or is that the graphical interface of the truth of what's going on behind? It's the graphical interface of something that is, you know, more absolute.
Yeah.
At the bottom of reality.
Yeah, it's a version.
Yes.
But it's not.
And so in space-time, we essentially have found the base level of where space-time can function. And it's called the Planck scale.